channel Mechanical Portal. In this lecture we are going to discuss various terms that will come across TS diagram, especially while we are focusing on power plant engineering or thermal engineering. After this lecture we will get a proper idea on how TS diagram is to be plotted and how we obtain values for enthalpy, entropy, etc., which ultimately makes problems from steam engineering easier. So let us start our session. TS diagram is basically a graph between temperature and entropy. Temperature and entropy. Temperature on y-axis and entropy on s-axis. In this graph I have plotted TS diagram for water. So at minus 10 degrees Celsius it will be ice, and at 1 atmospheric pressure, 1 atm, I am heating this ice from minus 10 degrees Celsius to 250 degrees Celsius, and I am observing the phase changes between these two temperatures. So the beginning is from minus 10 degrees Celsius where the phase is solid, that is ice. If we keep on heating at 0 degrees Celsius, it starts melting. So there is an equilibrium state where solid and liquid state coexist at 0 degrees Celsius to some extent, and after a certain heating, then the temperature increases from 0 to 100 degrees Celsius, and at this point 100 degrees Celsius again phase change occurs, liquid to vapor, and then completely becomes vapor. So in between these regions there is a phase changing region where heat is latent heat. Heat here is latent heat and heat here is sensible heat. Okay, this is basically a TS diagram. Now for different pressures, for different isobars, we have different plots. The variation is different. So I am considering this region where the variation occurs like liquid and vapor, these three phases. I have mentioned isobar. Isobars are actually thermodynamic process where pressure is kept constant. See this curve from 0 minus 10 degrees Celsius to say 250 degrees Celsius or any temperature. I am increasing, keeping pressure as constant. So this line is known as isobar. Okay, this is another isobar. This is another process where I have kept pressure constant. Now let's move on to TS diagram terminologies. So we are focusing the liquid plus vapor and vapor region. Okay, these are the isobars drawn at various temperature and entropy for a process. Okay, now I am going to connect these points. Okay, if I am connecting these points where the phase changes occurs, I will get a curve like this. Okay, so I am joining these points, and what I get is this saturated line. Okay, so saturated line is the line that separates single phase regions from two phase regions. So we have two saturated lines here. That's one saturated line separating liquid and liquid plus vapor mixture, and another vapor and liquid mixture. So I have mentioned two saturated line. So there should be a point which differentiates these two saturated lines. That is the point, critical point. So critical point is the point where saturated liquid line and the saturated vapor line meets. Okay, so we have saturated liquid line. This is the saturated liquid line. Saturated liquid line which differentiate liquid and liquid vapor mixture. We have another saturated vapor line which differentiate vapor and liquid plus vapor mixture. Also, critical point is the point at which liquid directly changes to vapor. There is no liquid and vapor mixture at a critical point. Critical point for water is 374 degrees Celsius. So at 374 degrees Celsius and pressure 22 megapascal, water directly changes to steam. Now we are looking subcooled liquid. Subcooled liquid is the liquid which doesn't attain energy to reach the saturation temperature or saturation point. So this is the subcooled liquid region. Here liquid doesn't receive any energy or doesn't have energy to reach the saturation point. Saturation point is the point on saturated line. So here we have saturated liquid and we have saturated vapor on vapor side. Okay. Superheated vapor is the vapor which receives energy more than the vapor at a saturation point. Dryness fraction. Dryness fraction is an important term which we will come across while we are solving problems in power plant engineering like Rankine cycle, reheat cycle. Okay, basically dryness fraction is defined as the ratio of mass of dry steam to mass of wet steam. So dryness fraction is defined, it's denoted by X and is mathematically given as mv by mv plus ml, where mv is the mass of dry steam and ml is the mass of wet steam. Now let us consider this point. Let this be point 1 and let this be point 2. This is the point 1 is on saturated liquid line and point 2 is on saturated vapor line. If we consider point 1, what will be the dryness fraction? Dryness fraction equal to mass of dry steam. Here dry steam is not there. Here this is the wet steam because water particle is there. So mass of dry steam, that is equal to 0 by mass of wet steam plus mass of dry steam. Anyways, this will be becoming 0. We have dryness fraction at point 1, that is in saturated liquid line as 0. Now we consider second point, that is dryness fraction at saturated vapor line. Here wet steam is the here dry steam is the wet steam equal to 0. No mass of wet steam will be found. So the equation will be like mv by mv plus here ml equal to 0. Now the value becomes x equal to 1. This is the dryness fraction at the saturated vapor line. So dryness factor is between the range 0 to 1. Okay. Dryness fraction is also called as quality of steam. We will hear this term in power plant engineering, quality of steam. Basically both dryness fraction and the quality of steam both are same. Now we will move on to the expressions for specific enthalpy and specific entropy. Before going to the expressions, we have three regions here. First one is subcooled region, the other one is superheated region, and the third one is liquid vapor mixture region. Vapor mixture. These are the three regions in a TS diagram for water. Now I am considering three points A, B and C. I am going to get the expressions for enthalpy and entropy at individual points A, B and C. These 3 points are at 3 regions, that is subcooled region, liquid vapor mixture region and superheated vapor region. Before going to the write the expressions, I will write down the subscripts that we are going to use overall in this lecture. F denotes the liquid region. Okay, F denotes saturated liquid. F denotes the values of enthalpy, entropy at a saturated liquid. Then G denotes similarly saturated vapor values, and the Fg denotes liquid vapor mixture region values. That is, if I say HF or SF, this is the enthalpy or entropy at a point F, that is on the curve saturated liquid line. Okay, this is SF. Similarly, this is SG. SG is the entropy on the saturated vapor line. Okay, that is the entropy of saturated vapor. Now let us consider the point A. At point A, what will be the specific enthalpy and the specific entropy? We know point A is in subcooled liquid region. Okay, keep that in mind. Now we know the basic thermodynamic equation. Change in specific enthalpy is equal to Cp into dt. Okay, here this is specific enthalpy. If it's enthalpy, then it will be like H equal to m into Cp into delta T. Here m is the mass. We are considering specific enthalpy, so m is not considered. That is specific enthalpy equal to enthalpy by mass. Enthalpy per kilogram is the specific enthalpy. We have this equation dH equal to Cp into delta T. We need the enthalpy at the A. We need enthalpy at the A. How we are going to express this is like this. We have, say this will be HA, enthalpy at A. We know enthalpy on saturated line, that is the standard value for each pressure. Each pressure we have different enthalpy. Okay, enthalpy of, for this pressure HF will be different, this pressure HF will be different. Okay, so we have two values, HF is known, HA is unknown. We need to find HA. So here dH, change in enthalpy, is HF minus HA. HA enthalpy will be lesser than HF, because if we attain a certain enthalpy, that enthalpy is delta H. If we attain delta H enthalpy, then liquid reaches saturation point. Okay, so HF minus HA equal to Cp into dt. Here Cp is Cpl, that is specific heat at constant pressure for this liquid region, into delta T. Here temperature change, this point is saturation point. Okay, then this temperature is saturation temperature, Tsat minus the temperature at point A is Ta, is equal to Tsat minus Ta. So at point HA, enthalpy will be HF minus Cpl into Tsat minus Ta. This is the equation. HA equal to HF minus, we are taking HA to the right side and Cpl into Tsat minus Ta to the left side, rearranging the mathematical equation. So this is the value. This is the important value we have to remember. Similarly, if I am going to consider SA, entropy at point A, we know the basic thermodynamic equation ds equal to m into Cp into log T2 by T1 minus log P2 by P1 into R, where R is the universal gas constant, P2 and P1 are pressure at state 1 and state 2, T2 and T1 are temperatures at state 1 and state 2, Cp is the specific heat at constant pressure. So we know P2 and P1 in this case, means in our TS diagram, is same because these are isobar. So this whole term will be changing to 0. Now we have this equation like this, ds equal to m into Cp log T2 by T1. Here T2 temperature at second point, which is the saturation temperature. So I can write this at saturation temperature Tsat by T1. Here we are taking point 1 or the first state as Ta. So we get the equation ds equal to m into Cp log Tsat by Ta. Now we are considering specific entropy. So we don't have to take mass. Similar case like this, specific entropy is equal to entropy per unit mass. Okay, we have SF and SA. So ds we can get it as SF minus SA equal to Cp log Tsat by Ta. This is the equation for change in entropy at a point A, that is in subcooled region. Okay, here SF minus SA. Here SF minus SA is the region in the curve SF minus SA. This is the point SA.